Okay, welcome to this lecture on applied statistics with an overview of factorial experiments. And this is covering chapter 15 or large parts of chapter 15 with 2 to the power k experiments in this book by Walpole, Myers, and Ye. The setting is as follows. We have effects or factors that we study at the low and high levels. So only 2 levels here, high and low. And of course, it's not always easy to set up high and low, but we assume that we can get high and low factors. And this is done for each of k factors. So in total, this gives 2 to the power k experiments where the factors are varied at their high and low levels, all factors. So even though there are lots of combinations here of factors high, low, high, etc., we will mainly focus on doing such experiments to estimate the main effects of certain factors and possibly some interaction effects. So overall, if we have 2 to the power k experiments, say k is 3, then we have 8 experiments. If k is 4, we have 16 experiments. Then from these experiments, we can estimate 16 effects in total, or 8 effects in total if k is 3. So that's one main effect. It's one mean, overall mean. It's k main effects. And then it's a number of first order interaction terms and then higher order terms. And in the end, one term where they are all interacting, all factors. But as I mentioned, we will mainly focus on the main effects and maybe the first order interactions. So let me explain this in a very simple example with just 2 factors, A and B, that are varied at their high and low level. And then we measure data here. So these are the responses for each case. Response, say Y, and in this case, Y is at high for B and low for A. So we can indicate that minus plus. Whereas this one is B high and then A is also high. So this is Y for the combination of plus plus, measuring at both high levels. And in total then, since there are 2 factors varied at high and low level, we have 4 combinations of high low, low high, low low, high high. And that means 1 measurement for each combination. Okay, so how do we then estimate the main effects if we start with this point? What we do is to estimate A hat, for instance, is to take the average high minus the average low. Okay, so that means we have 2 measurements here when A is high, one where A is high but B is low. So that's this one. And then we have one when A is high and B is also high. That's this one. And we take the average of these high values, looking at the measurements where A is high. And then we subtract the average low. So that means, okay, A can be low and B can be low. That would be this case. And then A can be low, but B high. That's the 40 here. And we take the average low. And if we go through this exercise here, we get 50 plus 70 divided by 2, and then minus 80 plus 40 divided by 2. And as we see, this is 60 minus 60. So there is no effect of A here. The main effect is 0. If A should have an effect, we should notice sort of substantially higher values when A is 1 compared with minus 1, at least when we average over all these different levels of B or C or D for that matter, if we have more factors. But this is how we calculate this. And we do the same for interactions. Then we take differences when they are simultaneously large or simultaneously low. So with an interaction term here, we denote this by AB hat. And this would be average high, average simultaneously equal, so simultaneously high or low, or averagely simultaneously different. So what would they be simultaneously equal here? That would be when they are both low, so that's here. And then when they are both high, because then they are both A and B are the same. And we take the average of this. And then we subtract the difference when they are simultaneously different. So that means minus, plus, or plus, minus, and the average. Okay, so this means that if we just plug in the numbers, we get here one, both are one, that's, or both are low, that's 80, and then both are high, that was 70, average, and then minus, plus 40, and then plus minus 50. And here we notice that there is a difference. So we get 75 minus 45, and that's 30. And what does this mean? It means that there's a positive interaction between A and B. It really makes a difference if they vary together or if they're different. And we can notice this if we plot the effects as we do here. Here A is at the low and high level on the first axis, and we have one line when B is plus, and we have one line when B is minus. And we see that when both are minus, we get very high values, but when we go to a different A, it goes down. And simultaneously, when they are simultaneously high, we get this one. And then when they change, so when A goes to negative, we go down again. So this difference causes an interaction. Here, if we have to work with negative A, it's also good to have B negative if we want a high response. If we have to work with positive A, it's good to have positive B if we want a high response. We don't get quite the same as with the negative one, but we still get higher than having the negative one. So then A and B interact. This is what we mean by interaction. And it's not so easy to visualize or to think about higher order interactions, but we get a similar thing. A, B, C can be combined in good ways to get a good response. Okay, so here we see two examples. One where there is interaction, that's the top one that we saw, and one where there is not so much interaction, actually zero interaction. So in this case, we see that the lines are parallel. So that means when A is low, it's good to have the plus, and when A is low, it's also good to have the plus, and the differences are the same. The lines are parallel. So here there's no interaction. It's a different example from here one, from the top one where there is an interaction. This whole thing about factorial experiments is very related to linear regression, where there is a particular type of design matrix. So remember that in regression analysis, we had covariates. So here we have an example with covariates. This might be x1 covariate temperature, and we have another covariate x2, which is concentration, and then we measure a yield. There are 4 measurements. That means 2 factors, 2 to the power of 2 is 4. And instead of having these regression parameters, we can sometimes index them at a high and low level. So this is necessary to go from regression to factorial experiments. And that's what's done here. You see temperature is low, high, low, high. Concentration is low, low, high, high. And that means we cover all levels of high and low, and we can index them as minus and minus, plus, plus for the different cases of high and low. if we do this kind of binary counting, we can then sort out all cases. So here we have the first one where they are both at the low level. So then there's actually a positive interaction because they vary simultaneously. Then we start counting here with a positive A, but still negative B, and then negative A, but positive B, and then both are positive. So we can list our experiments in all these combinations of 2 to the power of k experiments. And we notice the responses for each combination. So if this is done, we can either have this way of computing as just as we did with average high and average low, or we can look at this in a regression setting. And in a regression setting, we would then have to transform our covariates x1 and x2 into this form of -1 and +1. And that's easy to do. We just normalize this matrix. So instead of having this form of the least squares where we use x, we now work on a transformed kind of covariate. And that's always valid. We can still do our regression analysis, and we can make predictions, and we can study the effects of inputs. It's just that more terms go into the mean, and the slopes will not be the same, of course, because we have transformed our axis. So this is done here, where we have a new design matrix of ones and minus ones. And then we can do the calculation here for least squares analysis. And let's do this and see what we get, just to compare with what we just did with average high and average low. What do we get for the least squares here? So first of all, X transpose X inverse is simple because the different columns of this design matrix are orthogonal. If we multiply this matrix with itself, we will see that X transpose, what is really X transpose, then it's just shifted 1, 1, 1, 1, minus 1, 1, minus 1, 1, minus 1, minus 1, 1, 1, 1 minus 1 minus 1, 1. This is X transpose. So if we multiply this X transpose X, we will see that we first take the first row here and multiply with the first column, then we get 4. If we start multiplying this first column with the second column, we will see that we get minus 1, 1, minus 1, 1. So that means 0 when we sum these. And it's the same for others. So this becomes a diagonal matrix. If we multiply this one now with 1, we get 0. If we multiply it with itself, we get minus 1 squared plus 1 squared plus minus 1 squared, etc. So this is also 4. So this is a diagonal matrix because the columns of X are orthogonal. So that means here, what do we get? Well, we get 1 over 4 on the diagonal here. And then we have to form this matrix X transpose and multiply it with Y. And Y is then the response measured for each of these combinations of inputs. So here we have X transpose, which is then 1, 1, 1, 1, minus 1, 1, minus 1, 1, minus 1, minus 1, 1, 1, 1, minus 1, minus 1, 1. And we multiply this with Y, which is the different levels. So in the first measurement, we have A negative and B negative. So both are at the low level. This means we have Y minus minus. In the next measurement, A is plus, B is minus. So then this is Y plus minus. And then it continues going in like a binary count. Okay, so B would here be organized first as the mean effect. And that's what we see here. In the first row, we just sum all y's and we get the average. So the first one is simply y bar. We take the average. For the second B, that would be the effect of A. What's the effect of A here? Okay, and then we see we get 1 over 4 And then we have minus for the first one, and then plus for the next, and then minus for the next, and for the last one we get a plus. The plus and minus structure here is exactly what we need to get average high. So we see the plus here, A is plus when you have the plus sign. And we get the same for the B effect. So then we get 1 over 4, and then which ones are plus here? Well, we have minus, minus, and then plus. And now we see that the plus terms come when B is high. So this is exactly the same as what we just did with average high and average low. The only difference is that we divide by 4 here instead of dividing by 2. So these effects would be y bar and then what we had, but a hat divided by 2, b hat divided by 2, and then ab hat divided by 2, just like we had previously. And this illustrates the link between a factorial experiment where we compute everything at a high and low level and take the difference, and a regression model with transformed covariates to be -1 and +1 of that particular design. Yeah, so there's a clear link here that we saw. This gives the same thing. And when we compute effects, we will then get that this B is, as I said, y bar, and then we have a hat over 2, b hat over 2, ab hat over 2. So there's a clear relation. It's just a factor 2 because we take the factor 4 instead of 2, and this goes on to higher number of factors. So here's an example where we have not 2 factors, but 4 factors. There's a catalyst in an experiment, there's a temperature, there's a pressure and concentration, and we believe these affect the response, which is some efficiency in our experiment. So we vary them at high and low level and in all combinations of high and low levels. And this can be easily done in Minitab. And now there's no longer a clear order here. So I like this binary way of counting. So I like to start with this one where all are low, and then I continue with the same setting, but now this one has changed. So here you see catalyst has changed to 1, but all the rest are minus. And then I go on to look at the case where only the second column is 1 and so on. So that would be this one. Now we start counting. This is back to low, but this is high. And then we continue all the way to all being high. But when you do an experiment, you don't want to follow this deterministic, clear way of binary counting. Instead, you want to randomize the order that experiments are done so that you don't kind of improve as you go on, because then the higher levels would come at the end, especially for concentration. So you might get a learning effect. So if you randomize your order here, you tend to get better results. And this is done, and then you can compute the main effects either by high and low, as we see here, or by regression view. So this is the regression view, and this is the factor high-low view. And we can get the effects. And here we see the big effect seems to be the catalyst, maybe, the temperature, potentially this, and then maybe some interactions. Maybe this term, but there are no really big interaction terms when we go down here in this example. We can also visualize results. So here we see the effect of each factor going from high to low or low to high level. And of course, this is scaled according to the efficiency. So we see that the biggest jump here is in temperature. And there's some in catalyst, some in concentration, less in pressure. At the bottom right, you also see the interaction plots. And I said they are very far from parallel if you have interactions. And there's potentially some lines here, as we also saw in the effect, that might not be parallel. But overall, there's not that different from parallels. Maybe there's not so much of an interaction effect for this particular example. This regression model that we have discussed is having a part where you have covariates and regression parameter, beta, and then you have a noise term, epsilon. And this noise term, epsilon, is assumed to have constant variance, sigma squared, and it's assumed to be independent and usually Gaussian distributed. But if we have 2 to the power k experiments and we have 2 to the power k factors because we want to estimate all effects of A, B, and C and all these interactions A, B, ABC, etc., then we have no redundancy to estimate these the sigma squared. So it would be difficult to do the kind of estimate this, what would be this effect. And in a usual regression model, how did we estimate this? Well, we got B first, which was X transpose X inverse X transpose Y. And then we saw that the variance of B is equal to sigma squared and then X transpose X inverse. We didn't know this, so we could estimate it from the residuals. So we said estimate by S squared. But this is not so easy to do when there's no degrees of freedom left for SSE. We have 2 to the power k, or let's call this n, experiments, and we have as many factors. So what is done here is to either assume that there are some kind of replicate data. So that means we have many y's for each factor combination. So when we have set up an experiment in the lab with A being high, B being low, C being high, then we say, okay, now this is set up. Let's not only do one experiment, let's do 2 or 3. Then we get replicates. Then we change again to a new lab configuration. It takes a while. So when this is done, we actually do more than just one experiment. That's replicates. An alternative, if it's difficult to do replicates, is to say that these higher order interactions are just representing random variation, so we can use them to estimate this effect directly. So then we just estimate the variability of effects directly. These are 2 different ways of estimating the variance to say something about uncertainty and significance. There are also different methods, and Minitab actually use a method developed by Length, which is useful, but I won't present this here. It's based on some median of effects. Okay, so if we ignore the higher order terms, we got some redundancy to estimate the variance. So for instance, we can say, okay, we care about the main effects. So that means in our case, A, B, C, etc. D could be more. And then we care about first order interactions. So that would be A, B, A, C, A, D, could be more. B, C, B, D could be more. And then C, D. These are interactions. How do they vary together? So if we only care about those, and of course we care about the mean, then we have 1 plus 4, so that means 5. And then these are 6, so we have 11 parameters here. But we have 2 to the power of 4, we have 16 experiments. So now there's redundancy to estimate the variance, and we do it in this way. We take the average of these squared effects because we say their mean is hypothesized to be 0. and then we just normalize with the average here. So this is a standard estimate of the variance, assuming the mean is 0. Then, since we have estimated this, we can use the usual t statistic, the t distribution with this many degrees of freedom, 5 in this case, because we used 5 effects, to say if an effect is significant or not. So let's do this here, because from this printout, it's impossible to say if they are significant or not. We don't have any idea what the variance is. This was just plus and minus of all the different responses. And the plus and minus occurred in the way so that A was high minus low, or B was high minus low, or AB was high minus AB low. But we can't do this because it doesn't give redundancy. No way to estimate the variance. So if we ignore these effects, we can then, the higher order effects, we can then do this in Minitab. And that's what I have done here. So we can then go to Minitab and say, okay, we want design of experiments. We want a factorial experiment, and we have created this. So now we want to analyze this factorial design. So I choose effect as the response, and then I can select how many terms do I want to have in my model. And then we can start with 4 terms and see what we get. And we get this effect and the coefficient, that is the regression associate of the effect, but there's no standard error or no t-value here because we couldn't estimate them. There were n parameters and n data. So instead, let's go to design of experiments, factorial, analyze factorial design. But now we reduce the number of terms in our model. So let's say we only want the first order effects and the main effects and the first order interactions that are listed here. Then we can do this same thing. And now we suddenly get an estimate of the standard error. That is, we're averaging these effects that we thought were just random variation. And then we have a t-value. And we see that catalyst and temperature and pressure and concentration are all significant, have a low p-value, and potentially this temperature concentration interaction as well, which is surprisingly large given the variance we just estimated. So this is possible to do, and then we could also go on and reduce more terms, have only main effects. Let's see what we get then. Then of course things change because we estimate the variance in different ways, having only main effects. Now we get only the main effects, and we still see that they're significant, but maybe not pressure so much anymore, because now the variance estimate changed, and now it's not significant on this level. It's a different model. Okay, the other way to estimate variance is to look at the sort of connections here and go on the term directly, the replicate information. So then we have to be careful. What is the replicate variance? The replicate variance then is representing this epsilon variance. So it's not really representing the effect variance. There's a difference between the standard error of the coefficients or the effects and the standard variance of the residuals. So we have to discriminate between sigma squared and the sigma of the effect, and this is the relation. So if we then look at the estimates here, we will see that this estimated effect is linked to the standard error of the effect is linked to the standard error of the residual in this way, where we normalize according to this variance of the plus minus combination in the correct way. So this can be done using replicates. Then we take the average over all replicate runs. Here I'm assuming R replicates for each combination, and then I average to compute compute the variability in this kind of combination, and then average those over all factorial combination. It doesn't have to be like this. We could have some replicates for certain combinations and have difference, but this is maybe the most robust solution. Then again, it's the t-distribution. Suddenly this degree of freedom now change. Now we don't have just 5 degrees of freedom. Here we have a number of replicates. This would actually be 2 to the power k, and then r minus 1 for each one. We have a bunch of data that we use to estimate the variability. So this t-distribution has many degrees of freedom if k is large and r is large. Just like we have in regression and in particular in analysis of variance studies, we can choose to split the variance into different components. The total sum of squares is then comparing the data with its mean. We just take the mean of the data over all combinations. And this sum of squared error is looking at the sum over all data, but now we take the difference between the measurements and the predictions. And this regression sum of squares is then looking at the prediction minus the mean. So when we do sum of squares analysis, we see, okay, how much of the variability is explained by the regression model, or this model with the factors in there, compared with just the mean, which is simple to use. So if r here is near 1, it means that we have sort of good prediction from factors. If r is near 0, it means we are just as well using the mean. It doesn't matter so much. The factors don't really affect the response. We can just use the mean. But what is really nice about the factorial experiments is this orthogonality. So remember that this design matrix was orthogonal, and that also goes into this business. So now we have SSR that can be split in different factors. And this is very nice. So remember that SSR is computed as the difference between y hat and y bar, so the regression difference compared with the mean. And in our case, this prediction is then given as y bar, and then either plus or minus, depending on the design combination of factor A, and then either plus or minus, depending on the design combination for I, of b hat, etc. And the y bar is then always out of this SSR equation. And what we're left with is the combination of a hat, b hat, etc. squared, and then cross terms of these. But since this is an orthogonal design matrix, it will split out into these combinations where we have just the regression effects and then normalized by these sum of squares, which would be 2k, because this is orthogonal. So this means with a factor of 2 or 2 over n to 2 to the power k, etc., depending on the factorial view or the regression view, this is easy to split in different components because of the orthogonal components. And one other way to say this is to look at contrasts. Remember, contrasts was a linear combination of variables such that the sum was 0. And for all these combinations of plus minus, we have sum to 0 constraints. So each column, except for the first, which has the mean, and the mean goes out of SSR. So all these other columns have these sum of sum of contrast weights equal to 0. So in this way, we can also see that all these contrasts, they sum correctly to the SSR. They're orthogonal contrasts. So going back to the example, we can then split the variability into different components, split them into the mean component, to the main component, to the interaction components of first order, etc. And that's done here, where we look at the sum of square and split it in different components. And then we see that, okay, the total sum of squares here is about 1800. And then we have a model with 10 parameters. So that's, what's the 10 parameters? That's 4 main effects, because we have 4 factors A, B, C, D, and we have plus 6 first order interactions. And these first order interactions are listed here, A, B, A, C, etc., down to C, D. Because of the orthogonality, it's easy to see that this splits in components. And for the main effects, we have a big chunk of the 1600, and A and B are the main contributors here. The rest are not explaining much of the variability. For the two-way interactions, AB is explaining much of the variability. So perhaps AB, an AB interaction is a good model for this data set. That's at least explaining a large part of the variation, and those were the big significant effects. Yeah, when we do 2 to the power k experiments, we can do the analysis, as we've seen. We have to be a bit careful, because this is often done with very complex experiments that takes a while to do. So if we do one half today and the other half tomorrow, or one half in summer and then we take the rest in winter, we have to be careful about blocking. In particular, we want to block so that these effects can be estimated even though there's a block effect. So imagine that we do this, and down here, when we do a combination, plus, minus, minus, this is the same as what would have been if we have done it in the first block. But since conditions are better, maybe now it's sunny, so then we have a plus age. And that goes for all these combinations. They have a block effect age. And if we do not care about the way we're doing experiments here, then we could be in trouble. So why is this happening? Well, what happens is that if we in this case take a hat, what was this? It was average high minus average low. And when we compute this, we see that, okay, first for the high ones, it's this one, this one, this one, and this one. But the minus are also here. There's 2 minus here and 2 minus here. So both for the average high and average low, a block effect of age would cancel out, because it's the same for all of these. So it would cancel out. So that's good. That's good for the A effect. We can take the average in both terms, and an effect like age would cancel out. If we go to all others, here we also see this plus and minus structure, except ABC. So if we take ABC hat, and then we compute average high minus average low for this one, we will see that all the high ones are down here. So if we did the high ones here, we would not get this age. So the average high here is sort of age plus average high minus average low. So this becomes age and then plus the effect of ABC hat if no blocks. And then it's impossible for us to say, okay, we see this big effect of ABC when we combine all these measurements. But is it really ABC or is it just age we're seeing? They are some together, so it's difficult to tell which ones we're really seeing. And here we were smart because we blocked according to ABC. If we blocked according to A, so that means we took all the plus of A down here in the second block, we would confound A with the blocking effect. We would not be able to discriminate the A effect from the blocking effect. So this is important in blocking. And what is the rule then is to confound with blocks such that the higher interactions are confounded. Whereas the main effects and these first order interactions in this case are not confounded with the block effects. And again, we randomize within blocks so that we get no order effects. The whole thing about confounding is also important because we don't always have the time to do a full size experiment. Instead, we only have time or money to do half or a quarter of the experiment. And how do we then find the right half or the right quarter? This is not straightforward. And again, if we then choose only to do a fraction of the experiment, we have to come up with a good design so that we say, okay, we don't care so much about this here, but we really want to estimate the other effects. But perhaps you see some structure in this matrix. You see that, okay, A is nice, it's plus, minus, minus, plus, and B and C and so on have different structure. But then we see that AB is exactly the same as C. So if we only do 4 experiments here, we cannot really discriminate between these two. They are confounded. They cannot be discriminate them from AB hat. And the same goes for this one and the mean. They are confounded. Or A and BC, or A, C, and BC, they have the same sign, so we cannot discriminate them. They are confounded. So when we do fractional experiments and don't have time to do all experiments, we have to be careful what we're doing. And then the goals is again to estimate main effects and potentially first order effects, and to then do the confounding with the higher order interactions. And there's a whole way of thought around this. So in this kind of taxonomy, there's a lot of words around confounding or alias structure. And that's sort of which columns have the same signs. And there's something called generator or defining relation or contrast, which is the sets the structure of confounding. Resolution is also important, and it indicates which interactions you can get, what can you resolve in your experiment. So let's do one example on this. Here's a factor 4 experiment. So in real life, you should do 2 to the power of 4, which is 16 experiments. But we only do a fraction. We only do 8. So this is a 2 to the power k minus 1 experiment. But we can still estimate effects. We just didn't have time to do all runs. So we do some of them and make the best out of it. And here you see estimates of main effects, assuming that higher order effects are small. So if we see an effect, this is the main effect causing this one. It's not higher order. It's not interaction terms. We can still do this. We can also estimate the variability from the redundancy in the measurements. Or even using replicates in this setting, if that's easy to do. It might not be easy to do all experiments, but if we do a fraction, we can still sometimes do replicates easily. So here's a bigger example. where we have 7 effects. So these are a lot of effects. So then, of course, we don't want to do 2 to the power 7 experiments. It might be too costly. So instead, we can only afford 8 experiments. And how should we do this to be wise? Well, then we have some defining relations here, or a generator for the experiment. And that was ABC here, as usual. So then we set up ABC minus 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 plus minus 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 plus minus plus plus minus. I count in a binary setting. Of course, when I do the experiments, I will not do it in this order. I will randomize, but this is a good way of counting. So this is 8 experiments, and we let ABC vary freely. Now, when I come to D, I will say that D is confounded with AB. So I form D as the product here of AB. So that means plus, minus, minus, plus, plus, minus, minus, plus. For E, okay, what can I do there? I confound it with AC. So that means A times C plus, minus, plus, minus, minus, plus, minus, plus. And it continues to F and G. And since all these columns will now be different, we can actually estimate them separately. We can estimate all these 7 main effects, and we can estimate the mean from just 8 experiments. So that's quite nice. We managed to structure these plus and minus structure so that it's possible to estimate all effects. Okay, so I hope you got something out of this. And thanks for watching.